everyone, and welcome. Have you ever looked up at a giant skyscraper or maybe driven across a massive bridge and just thought, how on earth is that thing still standing? Well, today we're going to pull back the curtain on the incredible science of structural analysis. This is the unseen engineering that quite literally holds our entire world together. I mean, it's a question that's a mix of pure awe and, let's be honest, a little bit of healthy fear, right? How can something so massive, weighing millions of tons, be so perfectly stable? Well, the answer isn't magic. It's all about a deep, deep understanding of physics and materials. Okay, so let's dive right in. If we're going to understand how engineers pull off these incredible marvels, we have to start with the two most basic concepts they deal with every single day: stress and strain. I want you to picture stretching a rubber band.
You feel that, right?
The force you're putting on it is creating an internal fight inside the rubber. That resistance spread all the way through the material. That's stress. It's the material literally fighting back against being pulled apart or squished together. Now, as you're applying all that stress to the rubber band, it's obviously stretching. That physical change in its shape, well, that's strain. It's how much the material actually gives in under the load. And it's just a pure ratio, a percentage of change, so it doesn't even have units. So we get the forces at play, but how do engineers actually, solve for them? Well, it turns out it totally depends on the design of the structure. Is it a simple jigsaw puzzle, or is it something way more complicated? And this brings us to this idea of determinacy. Okay, so a statically determinate structure is the simple puzzle. You can figure out all the forces with just your basic equilibrium equations. But, and this is a big but, if one single piece fails, the whole thing could come crashing down. On the other hand, an indeterminate structure has extra redundant supports built right in. It is way harder to analyze, but it's also way, way safer, because other parts can pick up the load if one part fails. And this isn't just a vague idea. Engineers have a really precise way to measure this complexity. They use formulas just like these to calculate a number, the degree of static indeterminacy. Don't worry about the formulas themselves. The key takeaway is that this number tells them exactly how many extra supports a structure has, which tells them just how complex their job is going to be. And it's not just about the forces. Engineers also have to figure out all the different ways the structure's joints could potentially move around. This is called kinematic indeterminacy, or degrees of freedom. You can think of it like mapping out every possible wiggle, every bend, and every rotation in the entire skeleton of the building. So everything we've talked about so far is for forces that just sit still. But the real world? It's always in motion. Loads don't just sit there. I mean, a truck at the very beginning of a bridge puts totally different stresses on it than that same truck in the middle. To solve this moving target problem, engineers use this absolutely brilliant tool called an influence line diagram. It's basically a chart that shows them exactly how the force at one single spot on a bridge changes as a load drives across the whole thing. This lets them find the absolute worst-case scenario, the one spot to put a load that will cause the most stress, and then they design for that. And get this, there's an incredibly powerful shortcut for this, called the Müller-Breslau Principle. It's almost like a magic trick. It says that to figure out that influence line, all you have to do is imagine physically pushing or bending the structure right at the point you care about. The shape it bends into, that's your answer. It turns a really complex calculation into something you can actually see in your mind's eye. And that idea of a structure's shape being the key is so important. It's not just about analyzing forces. It's about choosing the right shape from the very beginning. And when it comes to spanning huge distances, one particular shape has been the undisputed champion for centuries. Think about it. A simple, flat beam just kind of sags under a load, which creates a dangerous amount of tension at the bottom. But an arch is just pure genius. It takes that downward force and cleverly pushes it sideways along its curve, putting the whole thing into compression. And materials like stone and concrete are unbelievably strong in compression, which is exactly what makes arches so powerful. But there's a catch. That brilliant redirection of force creates this incredibly powerful outward push at the bottom of the arch. It's called horizontal thrust, and you can see here the kinds of formulas engineers use to figure it out. Getting this number right is absolutely critical because the foundations have to be strong enough to contain that push and stop the arch from just spreading apart. Okay, so this brings us full circle, back to those super safe but super complex, indeterminate structures we mentioned earlier. How do engineers actually solve those puzzles? Well, they need some more advanced tools in their toolkit, and one of the classic methods is called the moment distribution method. This method is basically an ongoing negotiation between all the joints in a structure. Imagine all the forces are out of whack. What engineers do is they calculate the imbalance, then they release one joint at a time, letting it pass its stress along to its neighbors. Then they do it again and again, back and forth, until the entire system finally settles into a state of perfect balance. It's pretty cool. So far, we've kind of been assuming that materials are perfectly elastic. They bend and then they spring right back. But what happens if a force is so huge that it starts to bend the material permanently? This brings us to our last and maybe most important concept. Think about a paperclip. You've all done this, right? You can bend it a little and it snaps back, but if you bend it too far, it stays bent. It's yielded. But here's the key, it hasn't broken yet. There's still strength left. Plastic analysis is a method that lets engineers tap into that extra reserve of strength between when a material bends for good and when it actually fails. Now, to make sure this is done safely, engineers have to follow a strict 3-point checklist. The forces have to be in balance. Enough points have to yield to form what's called a collapse mechanism, and at no point can the force be greater than the material's absolute maximum capacity. This is the final safety check for a structure's ultimate strength. And all of this incredibly complex analysis, it all boils down to one critical number, the load factor. It's a beautifully simple ratio you see right here. It's the ultimate load a structure can handle before it collapses, divided by the normal, everyday load it's actually designed for. This single number, that's the ultimate measure of safety. So the next time you find yourself staring up at a skyscraper or driving across a bridge, hopefully, you'll see a little more than just steel and concrete. Hopefully, you'll see a symphony of stress and strain, of determinacy and influence lines, of arches and plastic hinges, all working together in a masterpiece of calculated safety, keeping our world standing strong. Thanks for tuning in.